Hi guys. Give me just a second before we start. My my daughter's having a problem. I need to find out what's going on. Hi guys. Sorry about that. My daughter is here too. She's taking remote classes and she needed help with something right now, so had to go off and take care of that. I think it's like we have a small class today. Okay, well, why don't we go ahead and get started? So we're going to continue on with chapter 1.7 today. We're talking about intersections, right? So we're talking about a line and a plane. We'll move our ways into like two planes, things like that. So let's go ahead and get moving on that. So yesterday we left off with, we had a line, which is our parabola, okay, intersecting a line here. And I'm sorry, it's raining and I've got windows open. If you guys can give me just 1 second, I have to go run around and shut the windows. Sorry, it's a little chaotic today between the weather and everything else. Anyway, thanks for your patience. Okay, so we did a line and another line. So one type of line and another type of line. And then we're going to take a look at example 6, which is all chapter 1.7. Example 6 is a line intersecting a plane. And we want to know, does the line intersect within the triangle on that plane? So we're giving, say I've got a plane, and the plane has a triangle on it. And I think you're missing stuff. You don't have enough information on here. So let's fill in the blanks on like what, like pieces of our triangle and our line equation. So we've got a line, we've got a triangle coming down here. And then the question is, here's our line. Here's our plane. And so we want to know, does the line intersect the plane and does it intersect in the triangle? Okay, so those are the things we're going to check out. So you need more information than what you have here. So let's add those pieces. So our line equation is given by this equation here, all right, our vector equation for a line. And then we have a triangle that's made up of points A, point 0, 0, 0, B, which is 2, 0, 2, and C, which is minus 1, 2, and 0. Okay. So you needed that information that wasn't on the questions originally. Okay, so what we're doing is we're using the triangle to help us build up a plane, come up with an equation for the plane. Okay, and then what we want to know is, you know, first, does the line intersect the plane, and does it intersect within that triangle? So the first thing I have to do is, given the points of the triangle, and I'm going to just randomly call this A, B, and C, so I can visualize it. I could plot it three-dimensionally and then actually graph it out and then see what things look like, but I'm not gonna worry myself too much about that. I just want to be able to kind of get a feeling for what this looks like. So in order to make a plane equation from this triangle, I think we kind of did stuff like this a little bit before. I'm going to think in terms of a displacement vector. Okay, a displacement vector between A and B, and a displacement vector between B and C. So I'll call that vector 1, which is going to go from A to B. Okay, which means I have to do terminal minus initial. So 2, 0, 2 minus 0, 0, 0, which gives us vector 1 as 2 minus 0, 0 minus 0, and 2 minus 0. And it gives me my vector 1. Let's do vector 2. So I'm going to do my second vector. It's going to go from A to C. Now remember, when I do these displacement vectors, I want to have the same initial point on both of these displacement vectors, so that when I do the rest of the math, it's keyed towards that initial point here. Now, it doesn't matter which point you choose as the initial point. I just happen to choose the one that has the most zeros in it. It makes the math nice. So terminal minus initial, minus 1, 2, 0, minus initial. This is going to look like minus 1 minus 0, 2 minus 0, and 0 minus 0. So now we have our two displacement vectors. Okay, now what I want to do is, I want to use these two displacement vectors to give me a vector that's normal to the plane. Okay, because I'm going to use that normal vector to help me write an equation for my plane. Okay, so if I think about my normal vector is v1 cross v2, remember? So remember, I've got two vectors and I do the cross product on them. I'm going to get a resulting vector that's perpendicular to both. And now as it happens, both of these displacement vectors are right on our plane. So when I get the normal vector, that normal vector will be perpendicular to the plane. And that'll allow us to come up with the plane equation. All right, so let's go ahead and do that. So I'm going to say I, okay, our basis vectors. Okay, so v1 goes first, 2, 0, 2. v2 goes second. And now I have to do the cross product. So I'm going to, you guys can try the cross product while I'm doing the cross product, and we'll compare answers. Okay, so you should get -4, -2, +4 as your normal vector. Okay. And remember, this is my plane equation. So my plane implicit equation, okay, is going to look like I can use the points. Let's do this. I'm going to do my normal vector. So if I say my normal vector has components A, B, and C, say A, x minus x naught plus B, y minus y naught plus C, z minus z naught equals 0. Okay, where x naught, y naught, and z naught are a point on that plane. Okay, I can use any one of those points that I want. I'm going to use the 0, 0, 0. It's nice because it's got a lot of zeros in it. So I'm going to say my A, which is, this is my A, B, and C. These are my coefficients. So -4 times x -2 times y plus 4 times z equals 0. Now I would be plugging in 0. So -4 times x minus 0 plus a -2 times y minus 0 plus +4 times z minus 0 equals 0, right? And then I multiply it out but anything multiplied by 0 just gives me 0. So this is my plane equation. I needed that. So now I can start thinking about the intersection of that plane right here with this line here. Okay. Okay. So let's see. So we've come up with our plane equation. Now I have to ask, does line intersect the plane? First, I'm going to ask if it intersects the plane, and then I'm going to ask, does it intersect the triangles? The first thing is, does it intersect the plane? All right, so I've got my line. I take my line and I say my x component is equal to 1 plus 2 times t. My y component is equal to 1 plus 1 times t. My z component is equal to 0 minus t. Okay. I'm going to plug this into the plane for x, y, and z. So when I do that, I'm going to get minus 4 times 1 plus 2 times minus 2 times 1 plus t plus 4 times a minus t equals 0. Okay. I distribute out all of these terms and I combine like terms, right? So let's go ahead and do this. I'm going to get minus 4 minus 8t minus 2 minus 2t minus 4t equals 0. Okay, let's combine like terms. Okay, so once I combine like terms and I solve for it, I'm going to get t equals minus 6 over 14, which I'm going to simplify minus 3 over 7. Okay, the t's are not canceling out. If the t's do not cancel out, that means the line and the plane intersect in some way. So this is a valid value. Therefore, line intersects plane. We want to find out probably where. What's the point of intersection? Okay, you guys, I'll give you a minute to finish writing that, and I'm going to flip the page. Okay. Like I ran out of space. Okay. Line intersects the plane. I'm going to continue it right here. Okay, so now I need the point intersection. I'm going to go back to my line equation. So my line equation was x equals 1 plus 2 times t, y equals 1 plus t, z equals minus t. And I'm going to plug in my t value into here. And our x, y, and z coordinate of intersection point. Okay, so let's go ahead and do that. So I'm going to say x equals 1 plus 2 times a minus 3/7. Y equals 1 plus minus 3/7. Z equals minus times a minus 3/7. Okay, 1 plus a minus 6/7 gives me 1/7. 1 minus 3/7 gives me 4/7. Minus a minus becomes positive. So my point of intersection is 1, 7, 4, 7, 3, 7. These are just numbers, right? Some kind of a decimal I can come up with, and I can plot that out. I'm going to go over 1/7 in the x direction, over 4/7 in the y, and then up 3/7 in the z direction, and that's my point of intersection. Okay. So my next question is, this is part B, is the point of intersection inside the triangle. Okay, so remember what that means is I have to think of the plane equation in vector form. Remember our plane equation in vector form was x equals, I've got a point on the plane, I've got first parameter T1 times my first vector, T2 times my second vector. If I have a triangle, and I'm trying to describe just the triangle, there's a relationship between T1 and T2, and that is T1 is positive, T2 is positive, and their sum is less than or equal to 1. And that puts it into a triangle. I create a line segment and a line segment, and then I basically make sure that they connect. Okay, it's a valid triangle. All right, so now I have to write out my vector, my plane equation in vector form. Well, lucky for us, when we created our vector, we came up with 2 displacement vectors. We created our plane stuff. We had 2 displacement vectors and the point that we were using. Okay, so this is our initial point. These are our 2 displacement vectors. So I'm going to remember, I'm going to write those down. I'm going to say V1 from before was 2, 0, 2. V2 from before, minus 1, 2, and 0. And then our point, I can't say that, point x naught equals 0, 0, 0. When I plug that into my plane equation, my vector form, I'll first write it all the way out so that you can see T1 times 2, 0, 2, plus T2 times minus 1, 2, 0, which is equal to, I'll get rid of the 0, 0, 0, T1, 2 plus T2 minus 1, 2, 0. So there's my vector equation for my plane. Okay. That's a lot of work, right? But we're good. We can get that done. Okay, so now what I need to do is I need to break this down into my x, y, z components. So I'm going to say x is equal to 2t1 minus 1 t2. Right, I got it from here. So I took all of just my x components. Okay, my y components, 0 times t1 plus 2 times t2. And my z is 2 times t1 plus 0 times t2. Okay. I'm going to set this equal to the point of intersection, because I want to know, is that point of intersection inside that triangle? This is my triangle, right? I put a limit on it. I'm going to see if I can make this work. So this is equal to x, 1/7. This is equal to y. This is equal to z. Right? This is our point of intersection we plug into here. Okay. Now I'm going to solve for T1 and T2. Which is basically like saying, okay, we know that this is on the plane. If T1 and T2 are a vector representation of our plane, which is equally valid as our implicit equation for our plane, we want to know what values of T1 and T2 are going to generate this particular point. Okay, and then we're going to check after we find that, do the T1 and T2 relate to each other this way? Okay, so when I solve for T1 and T2, right, so when I work it through, I'm going to get, right, so this is 2t2 equals 4/7. I divide by 2. I get t2 equals 4/14. Okay. T1 is the same, so I'm going to go 2t1 equals 1/7. T1 equals 1/14. Okay. Did I do something wrong? Oops. Oh, I had the. Sorry, folks. I made a mistake. It should be 3/7. I'm going to follow this equation here. 3/7. 3/14. I followed this one here. Okay. All right, so now I have T1 and T2. Okay, so now what I need to do is I have to check this criteria here to see if it's valid. So I'm going to go, let's see. Here's T1, T2. So T1 equals 4/14, which is greater than or equal to 0. Check. T2 is 3/14, which is greater than or equal to 0. Check. So let's add up T1 plus T2, and then see what we get. Okay, it's 2 and T2, so I'm going to go 4/14 plus 3/14, which is 7/14, which is 7/14. Oh, that's 1/2. Ooh, look at that, which is less than or equal to 1. Check. All right, so what that means is that our point of intersection is inside the triangle. Yes, I'll put it in big exclamation marks. Point of intersection inside our triangle. Okay. It's a lot of work, but it's good. We can do it. It's logical. We just follow our steps. Okay. Anybody have questions on? I know maybe seems overwhelming because we're doing a lot of different stuff here. I'll roll with it, right? We're just going to keep practicing this stuff. We've got this whole week to keep practicing, and then I'll work through some more ideas, and then we'll take a break and work on some classwork problems. Okay. I anticipate I have in the syllabus. I think that we start chapter 2 on Monday, but I think I'd rather keep reviewing for stuff. Maybe if we can keep continuing on chapter 1.7 tomorrow and on Monday, and then on Wednesday next week we'll just do a review for our exam. Okay. All right. So let's go into another example. This is 6. When I scanned it in, I know. All right. So example 7. Given that 2 planes are intersecting in a line, what is the equation of that line? All right. So let's I'm going to come up with a visual to see what that looks like. So I'm going to think about I'll draw this way. And I've got, here's my line of intersection, and I've got a plane kind of coming out. This, it's hard to get these things to look just right. You can imagine we draw these planes as finite, like pieces of paper, but unless we specify they're infinite planes, but I can't draw an infinite plane, so I'm going to draw them as little finite things. Okay, so now what I want is, see how these 2 planes intersect? This is our line of intersection. Okay, so just like when 2 lines intersect in a point, right, we lose a dimension from 2 dimensions to 1, or 2 planes intersect in a line. Okay, so it helps to visualize. Okay. So we've got our plane 1 equation and our plane 2 equation. So there's a bunch of things I'm going to strip out of here so I can kind of compare what's happening. All right, so so first off, my normal for plane 1 is the coefficient of my x, y, and z. So it's going to be 1, 2, and 2, right? So I pull out 1, 2, and 2. And then a point on plane 1. Right, so this is written in our generic form for planes. So I have a point here, right? I can just pull this out. This is point 1, 1. Remember, because it's x minus x naught, y minus y naught, z minus z naught. So it's the point itself is the opposite. So if this is a negative, then the point is positive. Okay, so that's for our plane 1. Do the same thing for plane 2. So my normal for plane 2, coefficients 2, 3, and 4. And my point on plane 2, I set up this problem so that they shared a point together. So the 2 planes share a point. Okay, so that means that that point, just pretend this is 1, 1, 1. Oops, there's a 1 in there. Okay, so if the 2 planes share a point, that means that the point is happening on their line of intersection. Happens on line of intersection. That's the only way they're going to share the point, is if it happens on the place where they're intersection of intersection. Okay, great. Okay, so let's do this. So what we need now is we need a vector, parallel to the line of intersection. Okay, so we can think about, I'm going to draw that vector in green. So remember when we do our vector equation, right? I draw it like I've got the vector that's on that line, okay? When I come up with the line of intersection, it has to be in vector form, okay? Because I have a point and I need a vector. So now let's visualize what's happening. I'll do this in purple. So when I do this, let's remember I've got a vector normal to this plane here, my P2. So I've got a vector normal to that, and I have a vector normal to this one. Okay, so this is normal 1, this is normal 2. Okay, so now what I'm going to do is to get a vector that's going to be perpendicular to both of those normals, n1 cross n2 is going to be equal to my vector. That's the vector on the line. Okay, so now that means I got to do a cross product. So I'm going to go I, j. Okay, and it doesn't matter if I go n1 cross n2 or n2 cross n1, it's just the vector points in one direction or the other. It doesn't matter. Okay, so n1, 1, 2, 2, and then 2, 3, 4. Okay, these are our normal vectors that we pulled out from before. All right, I'm going to do the cross product, and you guys can do it too, and then we'll compare our answers. All right, so this is going to look like I. Get 2, 0, minus 1 is your vector, which is the cross product of the two normal vectors. And now I have a point on the plane. This is the point that's shared between them. So let's write that down. So point on the line is the point that's shared between the two planes. And then a vector parallel to the line is 2, 0, minus 1. And then I can just put it into my vector equation for a line, x bar, x naught plus t times v. I'm just going to plunk it down in there. So it's going to be x bar equals 1, 1, 1 plus t times 2, 0, minus 1. There's my equation for the line of intersection between the two planes. Okay. A lot of stuff. We're going to do a couple more examples and then we'll start breaking for classwork. Right? Yeah.
How can we find like a point on the line, like the point on the line of intersection, the 1, 1, 1?
Yeah, it's a great question. So we're going to do an example in just a minute where you'll see that it's not quite so obvious. So the equation that I gave you, you can see when I take the point out of my equation and I take the point out of the other plane equation, it's the same point. So I actually set this problem up specifically so that I gave you a shared point between them. I gave it to you, right? On our next example, right, we're given two planes intersecting in a line, but you can see I can't extract a point. So we're actually, why don't I go through this example, because I think it'll answer your question, which is, what do we do when it's not obvious what the shared point is? We'll have to find that point ourselves, okay? So we're going to talk about how we're actually going to do that, okay? So I'm looking at example 8, which is, I've got two planes intersecting in a line, just like this here, okay, in that kind of a shape. But now you can see, based on the equations, I don't know what point. I have to find the point, find a point that's shared between the two planes, which makes this a point on the line of intersection. That's the only way they're going to be a shared point, because it's on the line of intersection. So let's talk about how we're going to do that. So the first thing I'm going to do is I'm going to extract out the normals to each plane. So my normal for plane 1, the coefficients of x, y, and z. So 1, 2, and 2. My normal for plane 2, 2, minus 3, 4. So I've got my two normals. The first thing I'm going to take a look at, just do a quick check to make sure that the planes are not parallel. Check, be sure planes are not parallel, because if they're parallel to each other, they're never going to intersect, and I'm not even going to bother, right? So how do I check? Do I check to see, check n1 parallel to n2, and I look, right, I've got 1 to 2, 2 to 4, that's the same scalar multiple, but 2 to minus 3 breaks that mold. So these two are not parallel to each other, which is true. Not the same scalar multiple from N1 to N2. Okay, so we know that they're not parallel, which is good. So that means that the planes are going to intersect somewhere. So therefore, the planes. That was my first thing. Okay, so I checked that. All right, so now what I need to do is I need to come up with a vector that's perpendicular to both normals. I'm going to come up with a vector that's parallel to the line, and then we're going to talk about how we get that point. Okay, so I need, so this was 1, 2, what is a vector on the line, which is N1 cross N2. It's just like we did before. So I'll set that up. 1 cross N2, and I'll call that B. So I, J, K are unit basis vectors. So N1, 1, 2, 2, 2 minus 3, 4. I'm going to do the cross product. You guys can do it too, and we'll compare our answers at the end. You should get 14, 0, minus 7 as your vector that's on the line. That's the vector that's orthogonal to both normals. Okay. All right, now we're going to talk about the points. This goes back to your question. So 3, point, point on the line. So for this, I'm going to need simultaneous equations. Okay, so I have 2 equations, one for each plane, but 3 unknowns, x, y, and z. So what I'm going to do is I'm going to set x equal to 0, and then I'm going to solve for y and z on both of those equations. If that equality doesn't work, then I'll try y equals 0, and then solve for x and z. If that doesn't work, I'll try z equals 0 and solve for x and y. One of them has to work in order for these to be intersecting each other. So let's write down what our steps are. So I'm going to set x equals 0, solve for y and z, right? So I set x equals 0. Now I have 2 equations and 2 unknowns. If that doesn't yield a solution, then set y equals 0, solve for x and z. So my point would be 0, x, y, or it would be x, 0, z. And then if that doesn't work, then set z equals 0, solve for x and y. If the planes intersect, you're guaranteed at least one of these 3 will work, okay? Because they have to intersect somewhere, okay? But it may not be with x equals 0. You don't know. You're just going to have to try it. Okay, so I'll try the first one, x equals 0. And I do x equals 0 first because I'm lazy and I go alphabetically. X equals 0, I do that first. So I'm going to go, I take a look at my equations, right? This is x plus 2y plus 2z equals minus 6. 2x minus 3y plus 4z equals 2. So I set x equal to 0 in both equations, and I'm left with 2y plus 2z equals minus 6 and minus 3y plus 4z equals 2. So I'm going to write that down. So I'm going to get 2y plus 2z equals minus 6. 3y plus 4z equals 2. Now, because I know I'm solving simultaneous equations, I stack them. So I can think about what I need to multiply by to get these to work. Oops, sorry, that should be minus 3. All right, so I'm going to look at, the y's are already set up positive and negative, so all I have to do is add them, but I need them to be same coefficients so they cancel each other out. So I'm going to multiply this equation by 3. So it will have that, and I'm going to multiply this equation by 2, and it'll look like this. 6y plus 6z equals minus 18. I have to multiply 3 into all of those terms. Remember, this goes back to like, would you have this in algebra 2? I can't remember when this would get taught. I'm going to multiply this by 2, 6y plus 8z equals 4. And I'm just going to add. So now the y's are going to cancel. 6 plus 8, 14z equals minus 18 plus 4 is minus 14. So then z equals minus 1. Very promising. If x equals 0, z equals minus 1, I'm going to plug it back into one of these equations and then see what I get. So I'm going to go 2y plus 2 times a minus 1 equals minus 6, and then solve for y. Y equals minus 2. So now I have x equals 0. So then the point that's shared between these two planes, these are equations for the plane. The point on the line that's shared between the two planes is 0, minus 2, minus 1. So that's how you would do it normally. Like, it was nice. Example 6 was set up right for us. We could just extract the point. It was perfect, right? It was made a nice example to think about. More often than not, you have to do this, where you have to find the point where they intersect, which is why if I'm doing this, I always do that quick check first to make sure that the planes are not parallel. Because if they're parallel, there's going to be no point of intersection. It's going to be frustrating when I go through all the math. So do this check first, right? That'll save you computational time, right? You always want to build in some kind of a check on this stuff. So they're not parallel. You can imagine if statements, right? So I'm going to have a module, right? Like a block subroutine that's going to check, are these two planes parallel? Like a Boolean, right? Are planes parallel? Yes or no? 0, 1. So if the planes are not parallel, okay, then go ahead and find the vector. So this is another subroutine, find vector, right? I'm going to pass in the two normals. Then my other subroutine is finding a point on the line, right? So I'm going to basically work through this, have a subroutine that does this too, okay? So now I can use these. I've got a point and I have a vector. I can come up with a line equation. Remember, it's x bar equals our point plus our parameter times our vector. So I'll fill it in. X bar equals our point, 0, minus 2, minus 1, plus t times 14, 0, minus 7. When you find the equation for the line that's shared between the two planes, that's the in line of intersection, that you have to write it in vector form. Okay. So far, so good. Did that answer your question, by the way?
Yes, thank you.
Great. Okay. So I'm going to talk about our next topic. And this is all still chapter 1.7. It's a big chapter. Really cool stuff. So also chapter 7. So part 2 is what we call closest distance. This is important, right? So say I have a line and a point, and I want to know what's the closest distance between them, okay? Or let's say I've got a plane, our line, a plane and a point, and then I want to know what's the closest distance between them, right? So I need to have some methodology for being able to figure out the closest distance. The closest distance is actually an important concept, right? You'll want to have some kind of a check in your programs, you know, when you're figuring out a trajectory or a path, what's your closest distance, right? So I'll teach you two methods, okay? And you can choose, I'll tell you which one I like better, but I'll show you two methods. We'll go through the steps, okay? And then we'll work it through. So let me draw this out a little bit better. So say I have a plane, and then I have a point off the plane. So it's important first to check to make sure that your point is not on the plane, because if it's on the plane, your closest distance is 0, right? So, right, I'm jumping, like if I've got this plane and I've got a point off the plane, the closest distance is the orthogonal, right? I'm just gonna go drop it right straight down to this, you know, normal here. So this is my normal vector. And then I have some point on the plane, x naught, y naught, z naught. That's a point on the plane. And then from here, I can come up with a vector. Okay, so we've got this closest distance from a point off the plane. You must check that. To a plane. And then you've got a point on the plane, which is x naught. A point on the plane. Now the point on the plane is not necessarily your closest distance, but I'm going to use this point, right? Just like we just found a point on the plane, I'm going to use this point here, right, to help me create a displacement vector. Okay, but we'll talk about how we need to do this. All right, so let me tell you the steps for method 1. You guys can choose which one you like better. So method 1 says we need the orthogonal for this. Sorry, we need this one is orthogonal projection. This one requires projections. Okay, so the first step that we need to do is pick any point on the plane. It's usually like one of your intercepts because it's the easiest one to get. Maybe you're given a point on the plane and you can use that, or you could just generate a point on the plane, but you're going to pick a point on the plane. Okay, now what I need to do is orthogonally project a vector onto my normal vector. Okay, V is our displacement vector between point on the plane and the point off the plane. Okay, so this method requires that we take this vector, our displacement vector, and we project it onto this normal. Okay. And our third step is get the length or magnitude of the projection. This will be, so like, let me write this in orange. So this here, right, this is our projection, this is our orthogonal. So this is going to be, that's our normal. We're going to get the orthogonal projection of V onto N. Okay. Get the length magnitude of our projection, and that will be our closest distance. Okay, that's method 1. And we'll do an example so you can see method 1. And we'll do an example of method 2. Okay. So example 9, we're going to use method 1 to begin with. So, example 9 says, show that the plane given by this equation here, x plus y minus 2z equals 4, does not pass through the point 0, 0, 2. So we want to make sure that 0, 0, 2 isn't sitting on the plane. Then we want to find out what's the point on the plane closest to this point here. So right, so we've got this plane here, and I've got this point 0, 0, 2. And then I want to be able to find out what's that point closest to the plane. So this is that spot that I'm looking for. Okay, and what's the distance between them? That's our closest distance between our point and our plane. Okay, so we're going to work through this using method 1, and then we'll come back and talk about method 2, which I like method 2 better, but I'm teaching them both, and you can decide which one you like. Okay, so part A. So does it pass through the point? Okay, so the first thing I need to do is I have to plug our point 0, 0, 2 into the plane and see if I get an equality that's valid. 0 equals 0, that's good. If I get 5 equals 0, that's bad. That means my point isn't on the plane. We'll see what that looks like. So I'm going to go 0 plus 0 minus 2 times 2 equals 4. So 0 plus 0, so minus 4 equals positive 4. Minus 4 doesn't equal positive 4. So no, point is not on the plane, right? Because our equality wasn't valid. If our equality was valid, if I got 4 equals 4, our point is on the plane. I'm not even going to bother the rest of it because the closest distance is 0. So what's the point in the plane closest to this point here? So my part here now is I have to get a point on the plane. I have to generate a point on the plane because, you know, the plane's pretty big. I need to figure it out. So I have to get a point in the plane. So I'm going to say, I'm going to go z equals 0, y equals 0, and then solve for x. It doesn't matter. You can choose x equals 0, y equals 0, solve for z. It doesn't matter. You're looking for a point in the plane. I'm just going for easiness. X plus 0 equals 4. X equals 4. So my point is equal to 4, 0, 0. That's a point on the plane. Now, that's not necessarily the closest point. This is our closest, this is our point in the plane. So this is 0, 0, 4. I'm going to draw it exaggerated, right? It's not necessarily the closest point. It may be, we may have gotten lucky, but mostly it's probably not. Because remember, there's an infinite number of points on this plane. All right, so now I have to create a vector from our point on the plane to the point off the plane. Okay, so we're doing this. We're creating this vector right here. Right, I need a displacement vector. Alrighty, so I'm going to go v equals 0, 0, 2 minus, oops, sorry, 4, 0, 0. Okay, so I'm going to get 0 minus 4, minus 4. 0 minus is 0, 2 minus 0. If I went the other way, it's fine. My vector would just be pointing this way. Okay, so now, okay, so to find a point on the plane closest to 0, 0, 2, I need the projection of v onto n. Okay, so remember, let's remember our projection rules. Projection of v onto n. So that's going to go, so v dot n over n dot n times n. Okay, so remember our dot product. So v minus 4, 0, 2 dot my n. Where did I didn't write down my n. So I'm going to write down my n up here. So my n is equal to 1, 1 minus 2. I just yanked out the coefficients of my my x, y, and z. 1, 1 minus 2. 2 dot 1, 1 minus 2. And all that gets multiplied by 1, 1 minus 2. Remember, we're coming up with a scalar multiple. So this projection now, and this is our projection. Right, so this is my normal vector, and I'm coming up with my projection. Projection of v onto n. Okay, so let's go ahead and do that. So minus 4 times 1 plus 0 plus 2 times a minus 2. Okay, so that's going to give me minus 4 times minus 4 plus minus 4 is minus 8 all over 1 plus positive 4, 6, and that's getting multiplied by minus 2. Okay, so this looks like minus 4/3. 1 minus 2 is our projection of v onto n. Okay. Whew, it's a lot of work, right? Wait till you see method 2, it's much easier. That's why I like it. Okay, so the point on the plane, okay, that's closest to our point in space, right? Now, the distance, let's see, what is the point on the plane closest to point 0, 2? Okay, so closest distance. So I'm going to answer part C first. So part C says distance between the plane and the point in space. Basically, I'm taking the magnitude of our projection. Magnitude of our projection, so minus 4/3, minus 4/3, 8/3. We take the magnitude of that, right? And I'm going to get, let's do the magnitude. So it's going to be minus 4/3 squared plus minus 4/3 squared plus 8/3 squared. Sum those terms up, take the square root, and then I'm going to get 4/3 radical 6 is my distance. Okay, that's the closest distance between these two. Oops, sorry, you can't see that. Whew, that's the answer to part C. Part B said, I'm going to go back to part B. Part B says, what's the point on the plane closest to our point off the plane? So that we're looking for is this point right here. We're looking for that point as we drop down. What's that point right there? So all I really have to do is I can actually just add these together and I can get it, but let's go ahead and work it through. So remember, if I say our vector, displacement vector is terminal minus initial, right? So if my vector is equal to my projection, so that's minus 4/3, minus 4/3, 8/3. It's equal to my terminal point, which is 0, 0, 2. That's my point off the plane, minus my initial. Okay. I've started at the plane. I've gone up to my point in space. I want to find out what's that initial point that's on the plane. So then I just add, and then I multiply by a -1 to get that point right there. So I'm going to add these two, and then I'm going to get point on the plane is equal to 4/3, right? So that's minus 4/3 plus 0 multiplied by -1 gives me 4/3. Minus 4/3 plus 0 multiplied by -1 gives me 4/3. 8/3 plus 2 multiplied by -1, I'll let you do the math, is minus 2/3. So this is the point on the plane that's closest to the point off the plane. It's basically this distance away. Okay, that's a lot. It's a lot of steps. Wait till you see the, I like that second method better, but you'll see why in just a minute. Give you guys a chance to finish writing that. You guys got that okay? Let me summarize our second method. We'll do method 2 here. Okay, but let me summarize what the method 2 is. So I've got a plane and I have a point, right? Now what I can do is I can say from my plane equation, what's my normal? Okay, so I've got this normal and I have a point. Now what I can do is I can say, I'm going to generate a line, make an equation for a line with point off the plane. We were given that. And vector parallel to the line equal to our normal vector, right? So look at this, I'm creating this line, right, based on my normal vector and the point that's off the plane. Okay, so I'm going to get this, it's going to be x equals x naught plus t times b, or t times, we'll call it t times n in this case. It'll give us an equation for that. Okay, now I'm going to find the point of intersection between this line and the plane, right? So I'm making a line equation. I'm going to find this point here, x naught, y naught, z naught. That's our point of intersection between the line and the plane, which we just did, right? We just did all those intersections, right? Right, so now I have, this will give me point on the plane closest to point off the plane. Okay, then to calculate their distance, the closest distance is now just going to be the magnitude of the difference between those two points. Distance is magnitude of the difference. This is our distance between those 2 points. I find it a little more simple, but it's up to you. You may like projections. You may want to be able to do that. I like the intersection idea better. Okay. I tend to do that one more, but we'll do them both. We'll do examples with them both so that you can see, and then you can choose which one you like better, which one you want to implement. Okay, so I can do the same thing, but with method 2. So now I'm just going to quick redraw this. So here's our plane. Here's our point 0, 0, 2. Right? And so I've got to come up with this normal vector. Normal vector. So my normal vector for here was 1, 1, minus 2. I got that, extracted that normal vector from the equation for the plane. Okay. And then our point is 0, 0, 2. So now my my line for this right here, this line that's intersecting the plane is going to be x bar is equal to 0, 0, 2 plus t times my normal vector 1, 1, minus 2. So I'm going to go through where does the line intersect the plane. I know it will intersect the plane because I'm creating it that way. Okay, so where the line intersects plane, it's like this. So I'm going to go x equals 0 plus t, y equals 0 plus t, z equals 2 minus 2t. I'm going to plug that into my plane equation, which they gave me at the beginning, which was our plane was x plus y minus 2z equals 4. So I'm going to plug that into here. So I'm going to go x, y is t, minus 2 times 2 minus 2t equals 4. Okay, so I'm going to combine all like terms, find my t value. So 2t minus 4 plus 4t equals 4. So I start combining. I'm going to get 6t equals 8. T equals 8, 6. Oh, that looks familiar, doesn't it? This is 4/3. It should look familiar. I'm going to plug it back in to find the point. Point of intersection. Okay, so x equals t, y equals t, and z equals 2 minus 2 times 4/3. So my point of intersection is equal to 4/3, 4/3 minus 2/3. Okay, that's my point of intersection right here. Okay. Now, to get the closest distance, I find the distance between this point and my 0, 0, 2. So my closest distance, right, is going to equal to the magnitude of 4/3, 4/3 minus 2/3 minus 0, 0, 2. Okay, that magnitude. Okay, so I'm going to go 4/3 minus 0 squared. 4/3 minus 0 squared plus minus 2/3 minus 2 squared. Add them all up, take the square root, and I get, voila, same thing. I should get the same thing. Different methods, okay, but you should get the same values, right? So this is my closest distance. Personally, I like this method better. It's a little bit more streamlined. It's using ideas that we've used before, which is points of intersection, okay? Phew, that was a lot, right? What I'll do is I'll scan in this stuff so far that we've done for 1.7 and then upload it onto our Canvas page for that module. Okay. Anybody have any questions on the stuff that I just did today? We actually don't have a lot of time for me to do classwork, but I'll spend time doing classwork tomorrow. We're gonna do reflections tomorrow, which is using a lot of these concepts. This is our last topic for 1.7. And then we'll have the rest of the class tomorrow and the whole class on Monday to just work through classwork, okay? And I can also answer questions on homework and stuff too. If you guys have questions, I also have office hours today as well. Okay. Everybody else set? Okay. All right, you guys, have a great day, and I'll see you guys tomorrow. Bye.